Okay, welcome back to Organic Chemistry. This is 2341, Introduction to Organic Chemistry 1, and we're going to be continuing on with stereochemistry today. If we look at our schedule right now, we have our, we did our activity on Friday of last week. We're going to finish up Module 5 today, and then we're going to start Module 6.1. Okay, six is actually kind of broken up into two sections there. I will assign the reading this afternoon as you can start to do that. And I will be doing, I will be uploading, changing the slides a bit, and so that I'll have those uploaded to both Top Hat and Canvas, hopefully by Wednesday at the latest. I'm hoping to get, oops, I'm muted. All right, can people hear me now? Was I muted? Okay.
No, I could hear the whole time.
I look like I'm talking. So, oh, that can happen, can it? All right. So let me go ahead and the slides for Module 6.1 will be uploaded probably on Wednesday morning. I'll see how far I can do, but we'll maybe a little earlier. But 6 is where we start into real hardcore chemistry. We're going to talk about mechanisms and different reaction types that we're going to be doing. So this is going to be where we finally gotten through getting all those necessary things out of the way, like how bonds work and how to name things. And we're actually going to get into chemistry. We're going to see things change from one thing to another. So that's the exciting part, and I'm really looking forward to that. Okay, so for due this week, I believe that all we have, let's see, this is week 7. So due this week, we have our homework for Module 5, since we're finishing up Module 5 today, will be due on Wednesday at midnight. You can go ahead and start doing the reading assignment in Chapter 6. And remember, that's also our homework for this week. We're going to look at that and try to start doing that. That won't be due until next week. So just go ahead and start with that first module, 6.1, and then start that reading, and I'll start lecturing on that on Wednesday. Of course, we have our Top Hat class, and I will be grading the activity today and hopefully uploading those grades sometime today or tomorrow. Okay, are there any questions about administration so far?
Are you going to put out Module 6 on the Top Hat?
So I hope you guys got to go outside a little bit this weekend. It was really pleasant, not too hot, not too cold, a little breeze. I thought it was really great. We actually ate dinner on the back deck, because it was so nice. So anyway, but I hope you guys got to do a little bit of that as well. Okay, so let me go ahead and, Ricky has a question. Okay.
Did you not hear me? Sorry.
Oh, yeah, apparently I muted my side somehow. Sorry.
Oh, sorry. Yeah, I was asking about Module 6 because it's not on the Top Hat yet.
Right. Right. It will be released today.
Okay.
I wanted to finish up with Module 5 before we did that. Okay.
All right. I just wanted to know.
Yeah. Look for it to be released by sometime this afternoon.
Okay.
At least the first part, 6.1. Okay, so let me go ahead and share my screen. Let's continue on with stereochemistry. And to remind you that our stereochemistry is about things that are identically the same thing. They have the same empirical formula and everything, but they only change by their position in space. That's the whole concept of stereochemistry, okay? So when we had these geometric stereoisomers, for example, things with a double bond, we did actually have different properties. But when we have things that have a chiral center or 4 different things bonded, typically to carbon, but it can be other atoms, we actually have exactly the same properties of boiling point, melting point, etc. The only difference was the fact that one would rotate a plane polarized light in one direction, and the other isomer would rotate in the equal and opposite direction. So that got us to this slide right here, where we have a racemic mixture. Racemic mixture is when you have equal mixtures of the 2 compounds. So one is trying to rotate the light one way, the other is trying to rotate the light the other way, and therefore it cancels each other out. And so we have 0 net optical activity, okay? And so when we have these mixtures, we call them racemic mixtures. That means equal parts, okay? What if we don't have equal parts? Well, then the one that you have more of is going to be rotating more of the light in that direction, and only part of it's going to be canceled out. So we have to have a definition for that, and we do. And that's called enantiomeric excess. Remember that pair of chiral compounds are enantiomers. And here, let me pause for a second. I gotta close the door, my cat's gonna come in. Sorry. Anyway, all right, so enantiomeric excess. That means we have one or the other one in excess. And what that means is this, 100 of these molecules are gonna rotate it this way, but if only 80 of these molecules are gonna rotate it the other way, then we get at least 20 of these molecules are gonna rotate our light, okay? So we can tell how much more of one than we have than the other by what we call enantiomeric excess. Do not confuse it with percent. It's not 80% this and 20% that. It is enantiomeric excess, how much more we have of one that allows us to measure that rotation. So the calculation is actually fairly simple here. We are looking at, we can do it by moles or by specific rotation, okay? So if you actually had the independent ones and you mix them together, you could do it by enantiomeric excess with moles. So you have the moles of the one isomer and the moles of the other isomer divided by the total moles. So what this gives you is that one of those is going to be greater than the other, and therefore you're going to have some percentage of that molar quantity there. However, you rarely know which one you have as which, so you typically do it by the enantiomeric excess we calculate from the observed specific rotation. Okay, so the way we do that is we have our percent enantiomeric excess, meaning the number of molecules that we do see rotate light and all the other molecules cancel each other out. We do that by what we see, what we observe, and we divide that by what it should have been for the pure enantiomer. So let's say we have the R and it's rotating it at a negative. So we have negative rotation of light, okay? And if it's pure, it has a number of like 20 degrees, okay? But now in our mixture, it only has a measurement of 5 degrees, okay? So we have that 5 divided by 20 times 100 is gonna give us our enantiomeric excess of 25%, okay? So that's kind of where we're looking at that, okay? So let's talk about why it's not actually percents of molecules here, okay? So the reason we like to do it with the calculated observed specific rotation is because that accounts for the number of molecules that are canceling each other out, okay? So let's look at that as in this box here. So let's say we had our S-butanol, and our S-butanol rotates it in the positive direction, so we call it the plus version of that. If we had 100% of just that ST-butanol, we would rotate that light 100% of what it should be, okay? So in this case, it rotates light to 20 degrees, okay? So we have our, okay, so this is in moles, okay? Yeah, so this is moles and that's the enantiomer, okay. So let's look at that in the function of moles right here. So that means 100% of it is that S isomer. So if we look at this right here, that means every single molecule in that solution is rotating light in the positive direction and they add up together to give us 20, okay? Now, let's say we just actually did about maybe 70% of our original number, which means we'll substitute 3 of the S's for R's, okay? What happens to our observed rotation, okay? So that means that for every S we have, every R we have, we cancel out one S. We cancel out an S and we cancel out an S. That means only 70% of the molecules available to us are rotating light. Therefore, it should be 70% of that rotation, okay? Now, in the case of if we have it where we have 5 mole percent, I'm sorry, we have 20, this is 25 mole percent here. That means we're gonna cancel out half of the S rotation molecules I mean, those 5 s rotation molecules, which means only 10 of them are going to rotate light in the positive direction as opposed to 20 here. So that means only half of that is going to be rotating light. Now, if we get an equal mixture of 1 to 1, that means they all cancel out. And we actually have an observed rotation of 0. Okay, and this is what we call our racemic mixture because we have equal quotients of it. Okay, now let's see how that percentage affects the measured optical rotation. Okay, so in this case, our S-butanol right here has an observed rotation of positive 13.52 degrees. Okay, now if we have none of the other material there, we have 100% of our compound, of our 100% of our enantiomeric excess, meaning we're going to have 100% of this rotation. Okay, which means our observed rotation for this sample here is going to be the 13.52%. Okay. However, in this one where we have 70% enantiomeric excess calculated by moles right here, we should only get 70% of that optical rotation. Okay, which means if we only have 70% of that optical rotation, we're not going to take it all the way to 13. We're going to back it off, and it turns out to be about 9.46%. I'm sorry, degrees rotation positive. Okay, by the time we get 50%, that's going to be cut in half. And when we have 0, when we have that racemic mixture, our optical activity goes to 0. Okay, so what this means is, notice the enantiomeric excess here is this calculation of the percent of the excess of the moles, right? Now, if we actually calculate it by percent of molecules, that's going to give us a different number. Here we have at 100% of molecules here, it's going to give us, there we go, our 100% optical rotation. If only 85% of the molecules are the rotating, but you got to count that 15% are going to be canceled out by this percent. That's why this number drops to 70. And that's why we only get 70% of the measured optical rotation for the pure enantiomer. In the case of this is 75% of the molecules versus 25% of the molecules, that means we are going to only have 50 because for every one of these molecules, we have to cancel one of those molecules out, dropping this to 50, meaning we are only going to get 50% of that optical activity. And by the time we have here that these 50 are going to cancel out all those 50, and we're going to have 0%. Okay. So what we see in enantiomeric excess is the percent of the molecules that aren't canceled out. Okay, and that's not the same as the percent of the molecules in the solution. Okay, it's the percent of molecules that aren't canceled out. So likewise, if we keep adding more and more of our other material, we can actually do the same thing with our other rotation. In this case here, we have our R, so we're looking for a negative rotation. And with half of the molecules canceled out, or 75% being the S molecules and 25% being the R molecule, 75% being R and only 25% being S, we actually only get 50% of our measured rotation. Notice it's negative, right? The S goes positive, the R goes equaling and opposite negative, okay? So that as we increase the concentration of R, we get a more negative number. And after we have a pure amount of R here, we get the full equal and opposite number, okay? So it's very important that you look at EE of the moles of one enantiomer minus the moles of the other enantiomer divided by that total moles, okay? It's not percent of the molecules. So it's kind of a weird calculation, but when you know that, you can take that percent EE, divide by 100, and then multiply by the pure one, and you can get the predicted observation of what that rotation of light will be. So you can also do it backwards. You can say, okay, I have a mixture that's not racemic, so it actually has an optical activity, and I know the pure one gives me a 20 rotation, but I'm only getting 10 rotation. that means that I must have a 50% enantiomeric excess because half of my molecules are not participating in the optical activity. So you can back calculate to the purity of your system by just measuring your optical rotation. In fact, that's probably the only way to measure it because all the other properties are the same. All right, questions on EE, percent EE, which is enantiomeric excess. It's not percent molecules, it's enantiomeric excess. And knowing the enantiomeric excess, you should get your calculated observed rotation. And if you have a calculated observed rotation, you can back calculate your EE and get to your enantiomeric excess that way. Nobody's muted. All right.
I had a question.
Yeah.
So in the nomenclature, it's S parentheses dash positive parentheses dash 2 dash butanol. Is that just to, like, for our aid in knowing that S is positive and R is negative?
In this particular case, S is positive and R is negative, okay? You have to measure it. There are other molecules where S will be negative and R will be positive.
So would we include the positive and negative in nomenclature, or only when we're like talking about it in a lab or something?
This is only important if we have a mixture of the two enantiomers, okay? We'll want to know which is which so that you'll know which is in greater concentration when you measure it. But if we're talking, if you just draw the compound, you won't know whether it's plus or minus until you measure it. So you'll
Cool. Thank you.
Okay. So that was, we talked about one stereo center. We talked about how to label it R and S. And we talked about how that you can't differentiate it except by the rotation of light, okay? So now we're gonna add a level of complexity to it. Now we're gonna have two stereo centers in the system, okay? So when you have two or more stereo centers, that gives you a different nomenclature, a different thing. So when you just have the one stereo center and you have those two molecules, that's a pair of enantiomers, okay? Now, once we go to that, now we're gonna have a set of diastereomers, okay? Diastereomers are anything with two or more stereo centers, okay? So let's talk about that. If you have two or more stereo centers, that means you're gonna have a larger number of possible structures, okay? And so there's a calculation that says that if you have 2 times the number of stereo centers, that's how many isomers you should be able to find, okay? So this means that if you have 3 stereo centers, you're gonna have 2 to the 3, so it's 2 times 2 times 2, meaning you're gonna have 8 possible isomers if you have 3 stereo centers. And then if you go to something like cholesterol, where it has 20 stereo centers, there's actually 256 different possible variations thereof, but we're lucky that the body only makes the one. Okay, so if we have 1 stereo center, we have 2 isomers. If we have 2 stereo centers, we have 2 to that power number of them. So in the case of this one with just 2 stereo centers, we know we have to figure out how to draw 4 isomers. Okay, 2 to the 2, 2 times 2 is 4. Okay, so how do we determine that? Okay, so one way to determine that is to use this kind of projection here, and so that it makes it easier to see where our mirror is and what we do here. So in the case of this right here, we can use this way of drawing the molecules to make sure we have all 4 isomers available to us from our 2 different stereo centers, okay? So in the first one, let's say we just draw one compound here, okay? Now in these type of drawings, this carbon and this line are in the plane of the paper. The one at the top goes back, the one at the bottom goes back, and these are coming out toward us, okay? So these are all coming out toward us. So these are the heavy wedges. So
that's just always like that?
In this particular projection, yes. Whenever you see this kind of cross-like structure, that's what this means.
Okay.
Okay. And it has a name for it. I just can't remember. It's like a Fischer projection. The name slipped my mind, but it's probably on another slide. Yeah, Fischer projection. Good. That's what I thought. I just wasn't sure. Okay, so let's do that same thing we did when we had just one stereocenter and draw the enantiomer of it using that mirror plane. So in that Fischer projection, again, we have these are coming out at us right here. Those are going back. And that being said, that means we can identify which is which. And in this case here, this one right here is our first, this is carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5, because that bromine's on the smallest number. So it says here that that's R. And so when we look at our perspective as seeing what we have here, we have 1, 2, 3, and so we actually have an R configuration, rectus or clockwise. Okay. Go ahead and do that off to the side, make sure that you can get that assignment correct. All right, so we have our one isomer, we have our perspective on where things are. So let's go ahead and draw our enantiomer by going ahead and putting our mirror plane in here. And we're just gonna do the closest thing to the mirror first. So we're gonna do these, and these again are still wedges, solid wedges, right here. The next thing we find is this whole line right here. So we have our CH3, our carbon, and then our attachment here. And then the last thing we have is bromine up here and hydrogen here, okay? Now, because we use that mirror plane, just like when we have one stereocenter, we used the Fischer projection to give us our two stereocenters in the correct place. Okay, so that's how we draw it, and that's what they look like. Now that we have our two stereocenters, and notice in this case here we had an R, and when we do our enantiomer of it, it turns into an S, and we had an R and it turns into an S, right? So if we do that translation correctly, they should always invert in their mirror planes. Okay. Now the first thing we need to think about is, because we use the mirror plane on this, that makes these enantiomers. This is our pair of enantiomers. They come in pairs, that's our pair of enantiomers. But we have a total of 4 isomers because we have 2 times 2, right? So how do we get the other one? Okay, so in the case of trying to draw the other isomer, what we need to do is we need to take one pair of one of the system and swap it. Okay, so what we've done is we've taken this R right here, and we're going to turn this into S. But we're going to keep this SS. So when we draw that, what we do is we move the bromine to the other side, move the hydrogen to the other side, and now this is now our 2S molecule, and therefore it's not the same as the 2R, 3R, and it's not a mirror image of this here, so it's a new isomer, okay?
No question.
Yes.
Is it just so? It just looks like you're trying to find all possible outcomes
Yes.
of the stereocenters, and will hydrogen always be the opposite, or is it just the lowest priority thing that'll always be the opposite
What do you
of the stereocenter?
Okay. Well, I still don't know what you mean by opposite. When we draw these fixed in space, right? You know, just that particular isomer has the hydrogens opposite each other. Oh, you mean like this right here, where they're opposite each other here?
Yeah.
Okay. No. When we draw this, you actually can be given this name here, and you have to draw it, and they couldn't be on opposite sides.
Okay, so you're just looking for all possible
Correct.
combinations.
Right. I'm trying to show you how we start with one molecule and we draw all 4 of the isomers.
Yeah. Okay, and then it would apply with like 3 too. You'd find all the possible options. It would always be opposite. R would always be opposite to S, depending on the mirror image, kind of.
Right. In the first pair, you're going to see whatever the stereocenters are, the mirror image is going to have the opposite of them.
Yeah. Okay, that makes sense.
So then to draw our third isomer, that's where we came over here, we have to swap 2 bonds. Now, the reason we do that is because remember, because they're fixed in space, by swapping 2, that means we've changed it to the other isomer. Okay. We don't switch more than one stereocenter. Okay, we do one stereocenter and one stereocenter only, which is what we see here, where this is, we only swapped this first one on this carbon 2. Okay, now that makes this not an enantiomer of these because we have our S and our R, so it's not an enantiomer. So it must have its own enantiomer. And so we do that same trick of drawing our mirror plane and go bromine, 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 the stick in the middle, and then the hydrogens are the too far out. So by drawing it that way, it means this is now a pair of enantiomers. Okay, and these are not like those are not non-superimposable. They have different stereocenters. So this pair here is, okay, this is going to be R. Because it swaps here, this will be R and this will be S. And so now we have drawn all 4 possible isomers here. Okay, now here's a clear distinction, okay? This is a pair of enantiomers. Enantiomers only come in pairs. This is a pair of enantiomers, okay? This is a set of diastereomers. All 4 of those is a set of diastereomers, okay? Now here's the definition here. Stereoisomers that are things that have all the same connectivity, but notice that our attachments are slightly different, so they're different place in space, okay? So when we have a pair of enantiomers and a complementary pair of enantiomers, all being along the same structure, just different in space, that pair of pairs is called our diastereomers, okay? And if you have 3 stereocenters, you have a total of 8 isomers. That entire set of 8 isomers are also called diastereomers, okay? So it doesn't matter how many chiral centers you have above 1, all the sets of the different isomers are called diastereomers. Okay. So let's look at that again, okay? So here's one where we actually have the wedges drawn to make it easier to figure out, okay? So the other thing to remember is when we have our set of enantiomers here, okay? And this is similar to the other one here. We have these 2 have identical physical properties except for optical rotation, okay? However, because this is different, because these stereocenters are opposite each other to make that pair of enantiomers, this set has 1 set of properties. Okay. Now, because we've swapped one of these, we've only swapped this top one and made its mirror image here, this pair has exactly the same properties as each other, but it can have different properties with its other isomer, okay? So what that means is that these right here can be separated from each other because they're gonna have different properties. These right here cannot be separated from each other using unless you use a specialized chiral separation technique.
So they have different physical and chemical properties?
They have slightly different physical and chemical properties if they're diastereomers, not if they're the enantiomers. These are identical, but if you had one of this set and one of this set, you could separate them by their physical properties.
Cool.
Okay, so notice this is just one of these and this is just one of those, and therefore you can separate them that way. All right, let's go back to that one. All right, so on to the next complication, okay? How we name them. Okay, so when we name them, we have to actually name all of the stereocenters in beginning of the word. And when we only had one stereocenter, we just had to use our S or R in a bracket, dash, and then what the name was, okay? But because we have more than one stereocenter, we actually have to identify which carbon that stereocenter is on. And so we note that with a number for the carbon it is, and then the R or S based on its stereochemistry of that specific chiral center, okay? So one way to do this when we have this Fischer projection is there's a different way where you don't have to redraw it, okay? So let me show you the technique for that, okay? So the idea here is that if you have a Fischer projection like this, what you want to do is you want to, in your head, rotate the hydrogen to the back here, which rotates the bromine to this side, like this, and rotates the methyl to this side right here, okay? So we've given it a perspective such that the bromine and the methyl group are in their same position. All we do is rotate them 120 degrees. And now we can assign our priority. So in this case, our bromine has priority 1. This carbon with multiple things on it is priority 2, and this is priority 3. So that gives us 1, 2, 3 counterclockwise, which gives us the S configuration, okay? So that's how you use your Fischer projection to quickly identify whether you have R or S. And for the other half of the molecule, which I will circle in green here, we do the exact same thing. Again, this is rotating to the back. This is rotating over here, and then this is rotating there. So we have, okay, actually, no, I'm sorry. The bromine is going to rotate over here because it's already in front. And then the methyl group, the ethyl group is going to rotate here. So the bromine is going to go over here, the hydrogen's going in the back, and the methyl group's up. So we're going to end up with our bromine here and our ethyl group here. And so that's what we see down at the bottom of the screen, okay? And when we assign our priorities, right here, bromine is 1, the carbon with all the stuff on it is 2, this is 3, and our hydrogen's back 4, so we have 1, 2, 3. We have clockwise, which means we have R, okay? So this was our 2 carbon, and let's go back up to here to show us why that's our 2 carbon, okay? So this is our 2 carbon, this is our 1 carbon, and this is our 2 carbon because it has the first attachment of something. See, this is a part of the chain to give us our pentane, but our number 1 carbon's here, which means our S assignment was on carbon number 2, 2S. Our R assignment was on the 3 carbon. So that's why we end up with the 2S, 3R dibromo, 2,3-dibromo pentane. Okay. And we can do, in fact, I would go ahead and after class, go ahead and practice being able to do that exact same thing to this one right here. Again, you're going to rotate this around, which means the bromine's going to come up here, the methyl group's going to be here, and assign R and S. And then for that, again, the ethyl group's going to come up here, the bromine's going to go over here, and assign your R and S. Okay. Sometimes people like this a lot better because you only have to rotate one thing 120 degrees and assign it. Okay. So that's one of the benefits of the Fischer projection. So
how come it's doing it to the, how come it's turning the top both times? If it's 2, if it's using different carbons, because it uses 2, what is it, 2R, 3S?
okay,
no, it's 2S, 3R. So
is which carbon in the pentane we're talking about.
Yeah.
So this has to be our number 1 carbon because if we name from this side here, 1, 2, 3, our first bromine would on 3, and then this would be on 4. So that means we have to name it from the other side to get 2 and 3 for our 2 bromine attachments. That's why our numbering system is, this is number 1. And that means our first chiral center is on carbon number 2, and we've assigned it S. And then the second chiral center is on our 3 carbon, which we've assigned an R. Okay, does that answer your question?
Yeah, it's just that, yeah, I think so. Because you just, when you're trying to find the R, you're still rotating the second carbon to try to find it.
Right. So whenever we quote rotation, we still haven't changed our priorities. We haven't changed our nomenclature. All we've done is got it into perspective where we can get the lowest priority in the back so we can do our clockwise or our counterclockwise.
Okay.
Okay. So go ahead and try it a couple times, and I believe there's a couple homework problems that do this exact same thing.
Okay. Well, if you're both using the second carbon, then how do you know that 2 is S and 3 and R if you're using the second carbon each time you're rotating?
No, the first one we rotated the top half.
Mm-hmm.
We rotated this part for this one right here. And then we rotated the bottom half for this one right here.
Oh, it's on the bottom. Okay, I was looking at them left to right.
Okay.
That makes sense.
No, this is the set you get to play with.
Oh, yeah, I was total. Okay, that makes way more sense now.
So
Okay.
yeah, because this is the 2 carbon is for this one, and this is a 3 carbon.
Oh, yeah, that's why. Yeah. Sorry, I guess I zoned out. Okay, well, thank you, though.
All right, well, let's continue on then. Okay. So, wow, this must be out of order then, because we can also use our Fischer projection if we just have one stereo center. It works best with more than one stereo center. So in the case of this, we can actually do this kind of projection here. And whenever you do a Fischer projection, what you try to do is you try to get your longest carbon chain in that vertical axis right here, and then you correctly assign where your groups are, okay? So that gives us our flat line Fischer projection with our longest carbon chain up and down, and then that shows us where our attachments are here and here, okay? So because of that wedge structure, we can simplify it in that Fischer projection because we do it the exact same way every time. Everything in that vertical hint is going backwards. Everything sticking out horizontally is coming out at us, okay? So that means we can draw these very complex molecules in a correct Fischer projection and know exactly what each stereo center is, okay? So I just said that. So let's do a conversion of this diol compound right here into a Fischer projection, okay? So if we just look at this right here, it's like, okay, wait a minute. I would always draw the hydrogens to figure out where the hydrogens are so that you don't forget them, okay? And so you don't end up accidentally swapping this. So the first thing I would do is I would draw our hydrogen here, coming out here, and our hydrogen going back here, okay? Now, the second thing we need to do in our Fischer projection is we need to get our carbon chain to be eclipsed because we want that carbon chain to be in a straight line, okay? So we have to rotate this bond around, which rotates our alcohol back and our hydrogen forward. So now we have our methyl groups right here. Our methyl groups, this chain right here is in the eclipsed form right here. And now we have all of our substituents pointing up, okay? So we have all of these substituents pointing up. Okay, so now if we put the eclipsed carbons right here in a straight line vertically, we end up getting, so imagine we're taking this methyl group here and this methyl group here. That means this OH is going to be on the right side. This OH is going to be on the right side, and the 2 hydrogens are going to be on the left side, okay? So the key here is you want to get that longest carbon chain up and down right here. And in this particular example, once we do that, we have our hydrogens are on the same side, just like they were in our eclipse position, pointing out at us. Our OHs are in that same position, pointing out at us. And in this particular model here, we can actually now see we have a plane of symmetry, okay? So if we have a plane of symmetry, that's saying that this particular one is a is showing us that we have a complication in here, and I'll talk about that complication on the next slide. But let's redraw the other isomer. So in this case right here, we had the 2R3S isomer. Let's go ahead and do the same conversion for the other isomer down here. This is the 2R3R, okay? So in this case here, you would of course put your hydrogen here and your hydrogen here. So in this case here, because this hydrogen is back and that hydrogen is back, when you rotate this methyl group down, this OH is going to end up being in the back and this hydrogen is going to end up being in the front. So when we draw our eclipsed longest carbon chain right here, we now have the hydrogen is still back for this side, the alcohol is still forward for this side, but these have now moved such that the alcohol is behind and the hydrogen is now in front. So now we want to redraw that such that the longest carbon chain is our straight chain right here, which means we have the alcohol and the hydrogen are going to be on one side, and the hydrogen and the alcohol are going to be on the other side. So to simplify it, we're going to draw it this way. And notice in this one right here, the top and the bottom don't look the same anymore. We have an OH and a hydrogen, so we actually don't have a plane of symmetry in this particular molecule. Okay, so when we use these Fischer projections, it makes it really easy to look for this plane of symmetry right here. And that plane of symmetry actually gives us a complication, because once you have a plane of symmetry in a molecule, it is no longer chiral. It becomes achiral. That's one stereocenter, two stereocenters, doesn't matter. Once you have a plane of symmetry, you lose chirality.
Stuff is hard to visualize sometimes.
Yes, this is probably the most visually demanding part of this. This is like Minecraft for chemistry.
Yeah.
Okay, so once you practice this, you can actually do the same thing where you can take a set of molecules right here. The first thing you're going to do is you're going to make the longest chain in the eclipsed form. Then that will convert it into your isomer here. And then from there, you get your Fischer projection. Once you have your Fischer projection, you can correctly assign R and S. Okay. Now that you have that isomer, you can now take your mirror plane and draw the opposite version. So it's chlorine, chlorine, hydrogen, hydrogen, methyls, methyl, hydrogen, and bromine here, which means this now is our set of enantiomers, because we drew our Fischer projection and we drawn our mirror image. That makes that a set of enantiomers. Now that we have that, we can actually convert it back to the other isomer and see that it's different in space. So notice the bromine and chlorine are both back on this one over here, and they're both forward on this one over here. So they are slightly different compounds, and if you flip them around, they don't work. So we have one set of enantiomers here. Okay. So just by switching one stereocenter from R to S, or S to R, in this case here, we now get a different isomer. And by drawing its mirror plane, we get its other enantiomer. So these are a set of enantiomers here, right here. And then when we redraw it out to its other sides through this conversion, stepwise conversion, we'll see that we have different compounds. So we have 1, 2, 3, 4 different isomers here. And here's how they're related. This pair here is your enantiomer. This pair here is an enantiomer. This set of all 4 are our diastereomers. So this is all 4 stereoisomers available to us in 2-bromo, 3-chloro butane. Okay, so I said before, diastereomers are any set of isomers with 2 or more, okay? When you have more stereocenters, you have more possible isomers. And for this example here, we're going to add another stereocenter. We have 1 stereocenter, 2 stereocenter, 3 stereocenters. Because if you go and start adding up the carbons and hydrogens attached, those are 3 different stereocenters. So let's draw 1 isomer here. And this one here is all of them pointing out. Because of priority, we end up with RRS. Okay. Now, since this is cyclohexanol, remember chlorine, it's a high priority thing when we're assigning stereocenters. But if it changes the name, that's where number 1 is. So that means this is our 1 carbon, this is our 2 carbon, and this is our 3 carbon here. Okay. So that being said, if we're all pointing up at us, even though our priorities are slightly different, and so we have RRS, all pointing down, they get opposite. And then 2 up, 2 down, 2 different up, 2 different down, and then the other possible set of isomers here. So we ended up with 2 times 2 times 2, which is equal to 8 stereoisomers available to us because we have those 3 possible stereocenters. Okay. And it's when one of the clever things about using the cyclohexane here is because the perspective doesn't change as you move these. The only thing that changes are your wedges. Okay, let's see. All right, great. Okay, so I said before, when we have a mirror plane in something, we lose chirality, right? And that complicates things when we have diastereomers. Okay, so in the case of this set of enantiomers here, right here, we have nice optical rotation. They of course have the same melting points and boiling points. And in this particular one, we had an RRSS as our enantiomeric pair. So if we were trying to draw the other 2 isomers, that we'd have to switch one of those to, let's say we switch this R to an S, and that gives us this isomer here. Okay. Now, to get our 4th one, we have to draw our mirror image. Okay. When we draw our mirror image, it ends up being that we have a mirror plane. Both of those isomers have a mirror plane. Okay. Now, because both those isomers have a mirror plane, that means we don't have 4 isomers. We only have 3 isomers because these 2 cancel each other out because neither one of these are chiral. 0 optical activity and a different physical property. Okay. So it is possible for you to have enantiomers that have diastereomers, but have, if one of those enantiomers that is related to it, it has a mirror plane, it's actually called a meso compound. And what that means is instead of having a total of 4 isomers, which we would have for that pair of diastereomers, we only have 3. Because the mirror plane complicates things, we lose chirality. When we lose chirality, that's the same isomer. And that's called a meso compound. Okay. All right, so this—
The bottom compound there those are both 1.
these
Sorry,
are
you're trying to say?
they're the exact same compound
Cool.
because they have a mirror plane. Because imagine if you took this R, let's see, for example, because of the mirror plane, you take this R and rotated it up, it goes to this R, this S rotates down to this S, and they are the exact same molecule.
Cool.
So
Okay.
when you have those 2 isomers that have that mirror plane, they are the same molecule and are not chiral. Okay. So doing that same derivation of all the different possible structures here, we can get to the same thing in this other isomer here, where we have, especially when we have this nice pair of enantiomers here, and then by just switching one of the chiral centers to get to the other possible set of enantiomers, we actually end up creating that mirror plane. Notice the bromines are on the same side now. When the bromines are on the same side, we have that mirror plane. That mirror plane makes it a meso compound, meaning we only have 3 stereoisomers for the 2,3 dibromobutane. Okay. Okay, so I'm gonna stop there because it's right at 10:50. I'm gonna finish up that last couple of, there's only a couple slides left, and it's all about the double bond. I'll finish up those at the beginning of Wednesday, and then we'll start chapter 6.1 on Wednesday. Okay, I'm gonna go ahead and stop recording.